So, hi, I'm Sebastián. The title of my talk is Reducing Feedback Pollution. I would like to start off with the overview of cheat compilation. So let's compile this simple sequence of code. The colors represents the types inferred by the compiler. The darker means less precise, as it's the combination of all other colors. And the add any instruction is the polymorphic add that handles multiple types. And at the bottom right, we see the type for the native add operation. Sometimes the compiler might be able to infer the type of some of the variables, be more precise, this integer in this case, for example, and then it will propagate this information and get more precise result types. So we can change the instruction to a more precise instruction. And if, on top of that, the type of the arguments match some native operation, we can also replace the generic operation at the native level with a more precise one. Now, this is not often the case. Sometimes we get the type of some of the variables, some not. So for example, in this case, we know the type for Y, we don't know the type for Z. And so what the compiler can do is try to guess the type. The assume instruction is the embodiment of this guess. And after that, the compiler can kind of resume the inference and restoring the precision for the next instruction. Now, if we fail, we de-optimize and resume in the unoptimized code. Now, we would like to improve this guess because the optimization is expensive. And one way to improve it is we can insert record instructions in the unoptimized code. So, for example, in the animation here, we will see Z is actually yellow when we run it, and we will propagate this information into the feedback vector on the right. Now it's empty, and now it gets it's yellow. And then now we have this information in the feedback vector. When we compile the function, we can use this information instead of just guessing. We can feed the compiler with this extra information and produce more efficient code, or hopefully the guess will be better than just randomly guessing. If we run the interpreter code for a while longer, we already encounter yellow, but maybe we encounter green in this case. And we'll also propagate this information here, and we will merge it with the yellow, hopefully something like purple. And if we continue running it more and more, eventually we'll merge all the different behaviors in this one place, and the feedback vector gets polluted. Now, on the other hand, if we compile it too quickly, after seeing too fewer types, what can happen is that the guess will most likely be wrong. So if you are assuming, say, we're expecting a yellow, but then we see green, and then we will de-optimize, and something similar will happen. We will de-optimize, we will go back to interpreter land, and we will pollute the type feedback as well. I think we can spot a pattern here where we learn something, compile for it, and then we see something else we didn't expect it, we de-optimize, and we recompile for something more general. And this goes on until the type feedback vector is polluted and there's nothing more we can do. So after that, the optimizations we can get from a polluted type feedback are kind of useless. So how can we mitigate this problem? Well, we could do once in a while, we could just zap the information and say, we don't want this type feedback to become stale. And once in a while, we're going to clear it. That seems reasonable. The problem is that a program can have many phase changes, and we will keep tripping ourselves and de-optimizing and re-optimizing all the time. So let's see what other people did in the past. So this once in a while could be more complex than just once in a while. We could have complex heuristics, that's what they do in Jalapeno, for example. Among other things that people do in V8, they delayed the collection of the feedback until the program stabilizes. And of course, we can always give up after too many de-optimizations. Another approach, rather orthogonal, is we can try to keep the information separated. And by separated, I mean we can store the information depending on the different context the program is running. And the context can be the type of the arguments, the call sites, even the call stack. And in this line, it's the truffle framework and the self-rewriting ASTs. Let's zoom in at the V8 for a second. If we inspect the state of a feedback vector of a function, and once in a while we clear the information, we will see something like this. We will encounter different colors. Looks nice. Now, if we don't zap the information, what we will get is something like this. Over time, after each invocation, after some time, the feedback gets more and more polluted. The idea of V8, they're working under the assumption that programs in JavaScript will have this unstable phase where they will see all these polymorphic types, and then after a while, the program stabilizes for fewer types. And then, having that in mind, if we delay the collection of the type feedback, we can just ignore all this, and then after this happened, we can start recording fresh, and we skipped all this polluted information. Of course, the programs need to fit into this pattern, which is not always the case, so it's not perfect. And just a few words for the self-optimizing AST interpreters. What they do is, in Truffle, is that instead of having feedback vectors, they store the information in the AST nodes, and these AST nodes get rewritten as they see different types, different information. So we start with empty feedback for this node, for example, and then later we see yellow, so we rewrite the nodes to now there's integer nodes, and then we see something else. Eventually, same thing happens, it gets polluted. So it's another approach, but the pollution is still there. Right, context. So before I get into our contributions, I want to explain context and contextual dispatch, and we will build on this later. This is prior work from our group from 2020. So as I said, one problem with speculation is after multiple uses of the same function, we will end up de-optimizing, recompiling, the code becomes too general, and there's nothing we can do. It's stale and stays like that forever. And also, de-optimizing itself, it's costly, so we would like to avoid that. So one thing we could do is we could have multiple versions of the same function. We can compile, for example, for V0, the general case. It supports all the types, but we can also create a version for, say, for the yellows. And notice in this case, we don't have any assumes. And all the information, all the optimizations are inferred from the context. So that's all we need. Now, all right, so we don't have the assume, but we have to have something else. Before we jump into the code, we need to check that the arguments we have in our hands are compatible with the versions we are going to call. So we dispatch, for example, say for, we call f of a and b. We inspect the arguments. We see they are yellow. We have a version compiled for yellow. We'll call it. And the code snippet we have in the middle kind of summarizes this dispatching mechanism. We inspect the arguments, we call it calling context. We dispatch, which means we look up the right version, and then we call this version we found passing in the appropriate arguments. So let's see just a couple more examples. We have the calling context on the right. We can dispatch to this version that matches exactly. Then this version only matches the brown one, and this version matches the purple one. So what I want to convey here is that the calling context don't need to exactly match the compilation context. They need to be lighter or more precise. And so as long as that happens, we are free actually to pick any version that fits. But of course, we want to pick the one that fits the best, because this is the one that more likely provide more benefits. Okay, we could always dispatch to the red one, but then there's no gains to be had. Let's see how the feedback vectors interact with the contextual dispatch I introduced. Let's say we are running the function now we start with the yellow, and we pollute the type feedback. We are running an optimized code, so we are recording into this feedback vector. Now we run for the green, and again it gets polluted. It gets purple. Now, if we try to compile a version based on this feedback vector here, let's focus on the version v1. You can see that if we compile for the yellow contexts, we can still compile and good enough optimized version. Actually, it's the same what you had before. And the reason is that all the information we needed was inferred from the code for the compilation context. In this particular case, we didn't need the feedback vectors. So because we have more precise information, so we can freely ignore it. And this last example for the contextual dispatch, let's make it a bit more complex. Now we have a global variable G, and also we are calling into a built-in ID. ID is just the identity function. It's a very, very simple built-in. The only characteristic of this function is a built-in, and the compiler doesn't know much about it. And the only thing it's how it doesn't know the type. The only thing it can do is just to probe the result at the end and see what it returns. And these two are stored in the last two slots in the feedback vector. Now, if we run this kind of client script on the right, we are setting the global variable first, and then running f, and then changing the value of g, and then running f again on a different calling context. Eventually, the feedback vector gets polluted, and again, if we want to now from this feedback vector recover the information, we can see that, okay, for the first instruction, we are able to produce efficient code, but for the rest, there's nothing for us to do. So we need to compile for the at any instructions. Everything is very generic. And this gets us to our contribution. So it seems that the problem is that we are storing all the information in the same bucket, in the same place. So let's see if we can improve the situation by adding more of them. The idea is very, very simple. Instead of a single shared feedback vector, we'll have many of them, one per call context. Those call contexts were the ones that were on the left. And we will use this specific context to compile the version at hand and to drive the optimizations. So let's revisit the last example with this new lens. We call F with the yellow context. We create a new feedback vector for it. We fill it in. Then we call it with a different call context. We create another feedback vector, and so on and so forth. And notice that here the last two rows, or the last two slots in the feedback vectors, are not polluted anymore, because its information is kind of separated, compartmentalized. And if we now try to produce a version based on, for example, for the yellow context, we'll see that we can now recover the type of G and W, and we can speculate on them, which wasn't possible before. All right. On the implementation side, I told you the idea is very simple, but the implementation proved to be a bit more complex. But basically what we want to do is, or the main focus is, we want to make sure that we record the information in the right places, in the right buckets, and then that we use the information correctly when compiling. We implemented a prototype on a just-in-time compiler for R, which is something that we do in our group, and it's also implemented on top of the contextual dispatch idea I showed before. Now, the problem is, so where do we store this new information? We start with we have a function f. This is the internal representation of the function. On the one hand, we have all the compiled versions for the different compilation context and a single feedback vector. We turn into another table which has multiple feedback vectors per calling context. And notice that these tables can grow independently, so they don't have the context don't need to match, or the size don't need to match, but it's more likely that the calling context will be bigger than the compilation context. So we will call it for more places that we compiled for. Now, how do we now store the additional feedback information before focusing on the where? The first thing we need to do is we need to have the so before it was easier because we always updated the same feedback vector because there was only just one. It's like a global thing we update. But now we need to have the call context available when we actually run a version, because there's no other way we can access to it. So we extended the dispatch mechanism that I showed before, and we also pass in the call context. And then we need to sort of patch all the places where we update the feedback information. One, for example, in unoptimized codes, that means that all the recording points, whenever we see the type of a variable, a callee branches, now the interpreter machine will have this call context available, and we are good. Now in native, it's different. In native, the only places where we update feedback vectors are on the optimizations. Otherwise, we never touch the feedback vectors. And there's two cases. The simpler case is when we optimize from the same function that we called, and for that we extended the signature of the native code, and we also provide this extra argument for the calling context, and so that this is information is available if we need to deopt. And kind of more complicated cases for when we deoptimize within inline code. And I want to get to that now. So the problem is as follows. So say we are compiling the f function for the brown compilation context, and while doing that, we are also calling g with x, so it's the same type. At least, I mean, at this point we only have like a static type, which is what we are compiling for. But now we want to inline g, and we inline g using the brown call context, because this is all it's all we have now. Because we are not writing the function, we're just compiling, and we need to compile the whole function. The only information we have is kind of static information, and this means that if we deopt from G, at least what we're doing for our implementation is we hard code the call context we are supposed to update if the optimization happens. And this is what we see here on the arrow. And let's look at this simple client code. Now let's say we call f with yellow, then we are calling also g with yellow, and say we optimize from g. Ideally, what we would like to do is to update the type feedback vector for yellow. That would be the right thing to do, the most precise one. And we didn't implement this solution, but basically what we would need to do is within the inline code, before the optimizing, we need to compute the current call context based on the arguments, and then the optimize for that. Of course, this is more costly because we're synthesizing a context when the function is optimizing. Yeah. So basically, we turn from a static thing that is hard-coded to a dynamic thing, but it's more precise on the other hand. Now the other problem is using the information that we recorded. So let's say we are compiling f, and the compiler managed to pick up precise information for x and y. And also now we want to inline g within f. But what happens if there is no feedback information available for the context yellow? In this case, we can pick a more general context. And in this case, we will pick the purple. So the question is if all the choices are safe, and actually they are safe because we can, everything we get from the feedback vectors is ultimately guarded in native code. So it's safe, but we want to pick the one that doesn't deopt too much and also brings some benefits. And lastly, for the merging information, sometimes we will compiling with a feedback vector which has some empty slots, some missing information. And for that, let's say there is some other feedback vector available for the same function with, let's say, complementary information. So we can do is we can merge this information into our feedback vector and compile for that. This is very abstract. In the paper we discuss different strategies, different heuristics for the merging. But that's about it.
Probably have about time for one, maybe two questions. Anyone would like to
So if I understand correctly, you are maintaining multiple versions for the functions, right?
Yeah.
So what is
I mean,
the...
that is prior work. We also maintain now is multiple feedback information for each of the versions.
Yeah, so what is the memory overhead if you use this approach?
So the contextual dispatch, what I showed initially, it's like this is our baseline. This is like the kind of the fundamentals of the compiler. For the the memory footprint, what we are our dispatch table that we use for storing the feedback vectors has up to I think 64 slots, because we can have lots of calling contexts, way more than compilation contexts. And also this is also the other problem, that the feedback vectors, we can have a lot of slots in each of the feedback vectors, because a function, it's recording everything it sees in the interpreter. So yeah, it can go out of hands. I don't have precise number, but it can go out of hands.
Thank you.
Yeah.
Question. So if you go back 2 slides, I'm not sure which slide. Keep going back 1, 2. Okay, that one. That one there.
Yeah.
The one after this. So in terms of merging new information into one another.
Yeah.
So there's contextual dispatch there. Plus you are also merging. So what's the overhead of actually merging these vectors together?
I mean, it can have some overhead. We didn't focus on the paper on the performance, because we were more worried about the kind of what we wanted to do is measure the pollution we have on a corpus of R, and then see if there are any if there's any space for optimization. So first we wanted to focus on if there is any space for reducing the pollution, and then we would focus on making it faster. The question you're asking is, okay, we are compiling, so we are not running native code, so we can spare some more time while doing that. Yeah, it's overhead, but it's overhead in compilation. It's not overhead running the native code.